Alright, so in this video we go over section 7.2, the inverse trigonometric functions continued, in which we are going to look at how to find the inverse trigonometric functions for the remaining functions. So in the previous section we did inverse sine, inverse cos, and inverse tan. In this section we go inverse cotangent, inverse secant, and inverse cosecant. So what we do in this, what we're also going to do is look at expressions that contain, these composition functions with combinations of sine, cosine, and tangent. So you will see how we talk about those. Okay, so let's define their domains and ranges of those new inverse trigonometric functions. All right, so the inverse secant function is defined for all x greater than or equal 1 or less than or equal -1. Keep in mind that this absolute value inequality means x greater than or equal +1 and x less than or equal to -1. All right, it means those two things, right? Well, actually, I believe this was this way, the other way around. All right, same over here. And the domain for the inverse cotangent function is all real numbers. Okay, again, need to change this. No inclusion signs for infinity. For the range as well, in this case we have that for secant function, the range goes from 0 and pi, but actually excludes pi over 2. The range of the inverse cosecant function goes from -pi/2 to pi/2, but excluding 0. All right, and in this case, the cotangent function goes from 0 and pi with no further restrictions. Also, it's worth to recall our reciprocal properties of sine, cosine, and tangent, in which sine is really the reciprocal of cosecant, cosine is the reciprocal of secant, and tangent is the reciprocal of cotangent. All right. So we're going to use this very often in this section when it comes to evaluate these functions, right? These expressions right here. So let's find some of the values of inverse secant, cosecant, and cotangent. So secant inverse of 1, well, that's going to be some value theta. So ultimately, we're looking for the angle whose secant is 1. Again, keep in mind that secant inverse of x equals y means x equals secant of y. So I'm going to rewrite this in the inverse form. So what I'm going to do, this is the same as saying, well, this is going to be our final answer here, but over here I'm going to write, this is the same as secant theta equals to 1. All right. And then this is the same as saying, well, we're gonna change this secant into its reciprocal, which is cosine. But the reciprocal of 1 is also 1 over 1, which is going to be 1. In other words, what we're looking here is which angle theta has a cosine of 1. Well, if we look at our unit circle, the only angle for which cosine is 1 is 0. We cannot say 2 pi because the function is not defined for 2 pi, only between 0 and pi. So in this case, well, what we need to do otherwise is, well, that angle is 0. All right. Cosecant inverse of 2. Well, maybe when doing the reciprocal here didn't make too much sense because the reciprocal of 1 is still 1. Well, so it's going to be more visual for the second example. So the angle So this is going to be some angle. The angle theta whose cosecant equals to 2. So this is the same as saying cosecant of theta equals to 2. But the reciprocal of cosecant, which is sine, we need to change this to the reciprocal. So we need to look for the angle whose sine is 1/2. And when we look at the unit circle, the angle whose sine is 1/2 is no other than 30 degrees or pi/6. Let's look at another example. Cotangent inverse of -1. Well, that's going to be definitely some angle theta, which we will figure out. So using the inverse note, the inverse property of the trigonometric functions, well, this is the same as saying that cotangent of theta equals -√3, which is the same as saying -√3/1. All right, but now just √3/1 might be a little bit tricky to find in the unit circle. So the trick is to write this as √3/2 over 1/2. All right, because ultimately these two cancel, giving us back this √3. Now recall that for the cotangent function, this is defined as x over y. In other words, we're going to look for the angle whose x is -√3/2 and y is positive 1/2. And if I look at the unit circle, well, that's going to happen at 5/6, where x equals -√3/2 and y equals 1/2. Right, so 5/6 is the final answer here. Let's look at one more. All right, looking at this one. So secant inverse of -2√3/3. Well, so let's see. So this is going to be some angle theta, in which, well, this means that secant theta equals to -2√3/3. All right. So now, how are we going to go about this one? Well, I'm going to change this to its reciprocal, which is cosine theta, which is -3/2√3. Well, in this case, this might be a little bit tricky to look, especially because we have the what's it called, the radical in the denominator. So you might want to rationalize and make it look a little bit better. So this is the same as saying, well, -3√3 over 2√3 times itself. Keep in mind that the root cancels. That's simply 3. Do not multiply. Just divide out the 3's. And final answer is -√3/2. Actually, not 3. So we're going to look for an angle whose cosine is -√3/2. So let's see. An x coordinate to be -√3/2 is again 5/6 or 150 degrees. Final answer. All right. Now on the next topic here in this same section, well, we are going to go over how to find values for other values that are not really as easy to find as in the unit circle, that is using the graphing calculator. However, in this case it's going to be a little bit tricky because, number one, the calculator doesn't have keys to evaluate inverse, cotangent, cosecant, and secant. And if we do 1 over tangent inverse, 1 over secant inverse, well, in this case, it's not going to work. Or I rather 1 over secant inverse, 1 over sine inverse is not going to work. So it's going to require a little bit more of work. And in some cases, well, especially for the cotangent inverse, let me highlight that one. Well, we need to keep in mind that the cotangent function and the secant function has the same range as in the cosine function. Alright, so when evaluating inverse secant, we can just convert to cosine just the same way we did it in the previous page, and then using the calculator. And to evaluate inverse cosecant, we just convert to sine inverse and we evaluate using the calculator. But the one that is going to be a little bit trickier is the cotangent inverse. Let me actually put a note here. Trickier. You'll see how we're going to go about that one. In fact, we will be in the need of constructing a circle of radius r in order to convert the inverse cotangent function to turn it into a inverse cosine function. You'll see how this is going to work. All right. Use a calculator to approximate each expression in radians rounded to 2 decimal places. So secant inverse of 3. This is going to be some angle theta that we will figure out, which we will approximate to 2 decimal places. So first of all, this is by inverse functions property. This means secant theta equals to 3. And in this case, I'm going to change this secant to its reciprocal, which is cosine theta. And we need to find the reciprocal of 3, which is 1/3. From here, what we do is solve the baby equation for theta. That means, or again using the inverse property of cosine theta, that is cosine inverse of 1/3. Cosine inverse of 1/3, that one we can evaluate it using the graphing calculator. And be sure that the calculator is set to be in radians. So what we do is simply secant cosine to get the cosine inverse of 1/3. In this case, we're going to get 1.23 rounded to the decimal places. That's good enough. 1.23, 1.23. So that's what we wanted to put in here. Letter B, cosecant inverse of -4. Well, this is going to be some angle in radians, whatever that is. We will approximate it to 2 decimal places. Well, using the inverse function properties, this means this can be rewritten as cosecant theta equals to -4. And in this case, I'm going to change this cosecant into its reciprocal, which is sine. But we need to write the reciprocal of -4, which is 1/4. And then doing the inverse properties, again, we get that theta equals sine inverse of -1/4. Okay, so in this case, that's going to give us, we just use a calculator in this case. So all we do is, where is it? Secant inverse sine of -1/4. All right, and that's going to give us a -0.256. Well, rounded to 2 decimal places, simply 0.25. Final answer. Okay, what about the cotangent ones that I was mentioning earlier, that they might be a little bit tricky to do? Well, so in this case, well, we still start by doing the same. Set it that equal to some angle theta. That means cotangent theta equals to 1/2. All right. Changing this to the reciprocal, which is tangent. That's 2 over 1. I'm gonna do 2 over 1. All right. So let's see. So in this case, we are going to construct a circle of radius r. Okay. In this case, keep in mind by definition, the numerator in the tangent function is y and the denominator is x. So that means I need to go to this point 1 comma 2, which is somewhere here. All right. But in order to find cosine, I need to find the radius of that circle. So let's find out what that is. And in this case, I'm going to write, we know that r squared equals x squared plus y squared. Well, we need to find r. R is going to be the square root of x squared plus y squared. So x squared, which is 1 squared, plus y squared, which is 2 squared. Well, in this case, 2 squared is 4 plus 1 squared, which is 1. 4 plus 1 is 5. Square root of 5. All right, so we need to change this to a cosine function. Again, in this case, we take advantage that cotangent and secant have the same range as cosine. So it is easier to work to rewrite cotangent in terms of cosine. I'll show you why in a minute. Why could be, in this case, if you just do inverse tan, it could give you a wrong answer actually. So cosine of theta equals, keep in mind in terms of x, y, r, cosine is x over r. And in this case, it's x, which is 1, and 2, which is actually not 2, it's root of 5. All right. So in this case, we use the inverse function property to rewrite. So theta equals to cosine inverse of 1 over root of 5. And in this case, this is going to give us approximately, so secant cosine inverse of 1 over secant root of 5. So that's 1.07. Well, that's 107. But we need to round this to 2 decimal places. Ultimately, this is 1.11. All right. So let's see. Cotangent inverse of -2, well, that's going to be simply some angle. Well, using the property of inverse inverse function, that's going to tell us that cotangent theta equals -2. And then, well, when using the reciprocal of cotangent, which is tangent theta, that's a -1/2. All right. So from here, I'm going to build another circle of radius r. Again, keep in mind that this is x, y over x actually. Okay, y equals to -1, and x is positive 2. Well, that's going to depend. Should y be the negative and x the positive, or should be y the positive and y the negative? Well, if the case is -1 over 2, that is y over x, y is negative, x is positive. Well, this point would be in the fourth quadrant. All right. Otherwise, if y is positive and x is negative, then we would be in the second quadrant. All right. Now we need to go back and check here that the inverse cotangent function has a range in the limit 0 to pi. That means second quadrant. All right, second quadrant. So we need to have x to be the negative value. All right, so I'm gonna have this point -2, 1. We need to figure out r, which happens to be square root of 5, for the same reason as what we did here. So let me do it again. R squared equals x squared plus y squared, and r squared, which is the square root of 5, quantity squared equals x squared, which is -2 quantity squared plus 1 squared. All right, and root of 5 squared. Well, actually, we need to figure out. Never mind, I was using something we were supposed to figure out. Never mind. X, or actually r, not x. Let me fix this. So that's r squared, r, and r. All right. So that's square root of 5 again. So in this case, well, we need to change this to cosine of theta, which by definition is, cosine theta is, again, x over r, which is the x value of -2 over r, which is root of 5. So to obtain the final answer, theta then will be cosine inverse of -2 over root of 5. And this will be approximately, well, when we do this in the calculator, let me just simply copy. That's let me insert a negative sign. Let me change this to 2, and that'll be 2.6279, which our final answer is required to be just rounded to 2 decimal places. That's 2.68. Well, why do we do all this when it comes to evaluating an inverse cotangent? I suppose that what we did for inverse secant and inverse cosecant. Well, let me use a different color for this. If you take it from here, well, theta will be tangent inverse of 2. And if you take it from here for the same one, theta would be inverse tangent of -1/2. All right. Let's see what happens when we do that in the calculator. So when we do this in the calculator, we do second tangent inverse of 2. In this case, we get 1.107, which is 1.11. In this case, we got the right answer. In some cases, it works. All right. However, let's look at the second case. On the second case, that's going to be inverse tangent of -1/2. And look, I get -0.463, which doesn't match our final answer in here. So when you do the homework, you may get a different answer. All right, so we're in trouble here. Well, actually, not -1/2. It's negative. Well, it's the same. Never mind. Yeah, because we changed that to cosine. So -1/2. So in this case, we don't get the exact same answer, that the 2.68 that we were supposed to obtain. In this case, we get -0.46, which is A very common mistake when we just do, oh well, change the cotangent to tangent by taking the reciprocal and then take the inverse tangent. Well, that works only for cosecant to turn it into sine and secant to turn it into cosine. But for the tangent, the tangent situation, let me put everything together here. It's not the same. So we're in trouble when getting, it works for some cases, it doesn't work for some other cases, unfortunately. Alright, so that's why I mentioned at the very top over here that that one is a little bit trickier to do. Alright, so let me move on to find examples, to find exact values of expression involving inverse sine, cosine, and cotangent, and tangent. So in the previous section we just did like sine of inverse sine, cosine of inverse cosine, tangent of inverse tangent, and vice versa in the sense of the compositions. Now in this case we're going to look at compositions having, having different functions, not the exact same function and its inverse. So different functions in this case. How do we go about these ones? Well, a good way to go about these ones is to replace this tangent as simply sine theta. Alright? In other words, inverse tangent of 1/3 is the same as theta. And then from here, what we're going to do is to construct a circle of radius r to finally evaluate the sine function. So ultimately, what we want to evaluate is a sine that comes from this inverse tangent. So what we do is, well, tangent inverse of 1/3 equals theta is the same as saying tangent theta equals to 1/3. And in this case, keep in mind that tangent is y over x. So this will be related to the point 3, 1, right? X equals 3, y equals to 1. So I'm going to plot the point 3, 1. Okay. Wait, it's actually 2. I thought it was a 3. Never mind. Need to change that. That's a 2. That's a 2. So this should be 2, 1. Alright, so I'm going to go to the point 2, 1, which is roughly here. And I'm going to need to find the radius r, which is by definition the square root of x squared plus y squared, which is square root of 2 squared plus 1 squared. We already did this one in the previous page, square root of 5. Okay, so now that we have everything r, x, and y, we're ready to evaluate the sine function, which by definition, that's a y over r from the first section in chapter 6 when we first defined the trigonometric functions. Sine is the y coordinate, and it's related to the radius as well in this form. So y, which is 1, and r, which is square root of 5. But well, this is a good final answer. However, you might want to rationalize the denominator. So that's going to be root of 5 times itself. The radical cancels. The denominator is simply 5. And root of 5 at the top. So root of 5 over 5 is our final answer. Let's look at another couple of examples. Well, we do the same. Ultimately, we want to evaluate a cosine to obtain a cosine. That is some kind of x over y in this case. In the previous example, we were looking for some y over r. We do an x over y this time. So this is cosine of some angle theta, in which we relate this whole thing as a sine inverse of negative 1/3 equals theta. using the inverse property, inverse function property, this is the same as saying sine theta equals negative 1/3. And in this case, what do we have? Y over R. All right, we have y over r. Well, in this case, we have a negative number. Which one could be the negative? Keep in mind the radius of the circle is always positive. It can never be negative. So y has to be the negative value. So in this case, what we're going to look for is for a point that has a y value of -1, an x value to be determined, and a radius r of 3. All right, so in this case, there's an x here to be determined and a -1 for the y value. Let's find out what the x value is. So r squared equals x squared plus y squared. So r squared, which is 3 squared, and x squared, which is to be found, and y squared, which is -1 quantity squared. So that's a 9. X squared plus 1, that's x squared equals 9 minus 1. That's an 8. And x equals the square root of 8, which reduces nicely to 2 root of 2. So 2 root of 2 is the x value in this case. So now we have the information to evaluate the cosine function. By the way, cosine function is x over r. X is 2 root of 2. R is 3. 2 root of 2 over 3. No rationalizing required in this case. We're good to go. Last of this set of examples in this topic. Well, we're gonna evaluate tangent of cosine inverse of -1/4. So again, we use the same trick, tangent of some angle, in which we will replace all this with tangent. So we're gonna write cosine inverse of -1/4, and that equals to some angle theta, which really means that cosine theta equals -1/4. And by definition of cosine is x over r. Again, which one is going to take the negative? The x, because the radius r is never ever it's never negative. So I'm going to go to a point in which x is -1 and y we don't know, but the radius is is 4. So I'm going to have the point -1 comma something. Okay, we'll figure out the something in a minute. So r squared equals x squared plus y squared. Now we need to figure out the y. So r squared equals the 4 squared and then -1 squared. 16, 1, y squared. I'm going to subtract 1 to both sides to get 15. And take the square root on both sides. And I know what you might be thinking. Well, when we take the square root, I didn't put the plus sign in this case. The plus minus sign. Because in this case, well, you can leave it unless you're looking for a negative value that you know that the value is negative. Well, in this case, or if you prefer, we can put it plus minus. But in this case, since x in the previous example was positive, take the positive. Over here on the second example, if we put the plus minus sign, well, our y value goes up in the positive direction, so we take the positive as well. All right, take the positive only. So in this case, square root of 15 is the y coordinate of this circle of radius r. In this case, r equals to 4. So now we have all the information to find the tangent function, and in this case the tangent function is defined as y over x, where y is the square root of 15 and x equals to -1. Simplifying these two quantities, negative root of 15 is the final answer. Alright, so let's just look at a couple of examples that, well, write trigonometric expressions as an algebraic expression that does not contain the actual angle. Well, so this will come later, a little bit later than sooner, when you take calculus 2 and when you do something called trigonometric substitution. So that's something that we do a little bit in pre-calc, just so you get an overview of what you will be doing later in your mathematical curriculum. So essentially we do the same. Instead of having a number here, we're just gonna have a value of u or x or your favorite letter. In this case, typically for this kind of examples, we use the letter u. So sine of tangent inverse of u, this means sine of theta. All right, but again, we are going to replace, we're going to relate these two, and we are going to write tangent theta equals, actually tangent inverse of u equals theta if and only if, which means tangent theta equals to u. All right. Now the tricky part when it comes to writing these expressions, I highly recommend you write this u as u over 1. Why? Because this way we can write this as a ratio. This is y and this is x. And this will give rise to the point 1 comma u. Whatever that u is, doesn't matter. It's an expression actually, not a numerical value. So I'm going to go 1 comma u to the point 1 comma u. Okay, and I need to find the value of r. We are going to find the value of r by using the Pythagorean theorem. Essentially, r squared equals x squared plus y squared. So r equals the square root of x squared, which is 1 squared, plus u squared, which is y squared. And in this case, 1 plus u squared is going to be square root of 1 plus u squared. Alright, now we need to evaluate this sine function. Sine by definition again is y over r, where y is u and r is this radical function. I know you might be thinking, well, what are we doing? What are we essentially doing? Well, we are writing this expression that is given in trigonometric form into an algebraic expression that contains only u. So when you take calculus, you will look at this, but instead of having a radius of r1, you will turn this into a triangle. A triangle in which x is 1 and u is y. And then you will do, however, the reason why I didn't do it the triangle way is because, well, the whole, what the textbook does for us is to look at the values of the trigonometric functions in the sense of circles of radius 1 or unit circles. But later in the semester we will do a little bit of triangles. But when you took when you take calculus in the future, you will get back to see this, but in the sense of a triangle. Let's do another example. Tangent of cosine inverse of u. So tangent of cosine inverse of u. So this is the same as saying some tangent of some angle theta, which we will figure it out. Right? Again, I'm going to relate these two, and then I'm going to write cosine inverse of u equals theta, which means that cosine theta equals to u. But again, u is the same as saying u over 1. Alright, so be careful in this case. Now, the definition of u in terms of x, y, and r, well, cosine is x over r. Alright, so the point that gives rise in this case is the point u, which is x, comma something, which is y. We need to figure that out, and the radius is 1. So u, the point u, comma something, r equals to 1. So we need to find the y coordinate of this point in the given circle. Well, so r squared equals x squared plus y squared. And in this case, well, we're looking for the y squared, so r squared equals 1 squared. X squared, which is u squared, equals y squared. So u squared, I'm going to move it to the left hand side, or actually I'm going to isolate the y squared. That's going to give us 1 squared, which is 1 minus u squared, and y equals the square root of 1 minus u squared. Alright? So the square root of 1 minus u squared. The square root 1 minus u squared. And finally, we have all the information to evaluate tangent. By definition, tangent is y over x, and y, which is the quantity that we just found, and x, which is simply u. And that's final answer for this, and I think it's also a good place to quit. This covers this section. I will see you in the next video.